All right, you guys. Well, let's do this and then we'll be good to go. Okay. Um, one more. Okay. Yeah, I hope you guys had a good week. And I hope Halloween was good-ish. Or I hope you enjoyed it. It was cold. It's been cold, but I think it's going to get a little warmer. So that's good news. Um, I hope you all had something delicious or will have something delicious for election night dinner because I'm very excited for my fajitas. So let's do it. Okay. So a couple of things, just due dates and other things. Okay. So test corrections for exam 2. There is an assignment ready to go, so you can do your corrections whenever you're ready. The exams were like not bad. Like the average was better. I feel like we're doing a little better. Hopefully, wherever you're at, I tried to get all the grades basically up to date. I still have to get the Beers Law Lab in, but I think except for Amanda, I still got to do your chromatography lab, I think. I got to check on that. But all that stuff's in. So hopefully you have an idea of kind of where you're at. This is about, halfway. I think there's 14 total classes. We do still have 2 more exams and the final. The final counts as 2 exams in itself. So that's kind of 4 more exams. But I think, as sort of a little tough love, you need to make sure that if you are right now in a place grade wise where you don't want to be, right? Maybe it's too low, and you need to bring it up. That's going to require more effort than you have currently been putting in, because if you have a low grade, and I'm not saying you're not working hard, don't get me wrong there, but you gotta do extra practice, do a little bit more, make sure you're on top of things. It all is not lost, but this is a point in the semester where we need to really just try to, work harder, because this is hard, you guys. Like, this remote stuff is harder than I anticipated to teach. So I can only imagine what it's like on the other side, where you're trying to pace yourself, and this is how we meet, and this is our interaction, and it's hard. I do try to answer emails as soon as I get them. Sometimes I honestly, I get so many emails that, like, if I don't respond in a day or whatever, like, just shoot me another email, because it probably just got buried. I'm not ignoring you. So that being said, exam 2 corrections are ready to go. You can correct the multiple choice and then 2 free response questions. So you can, same format, you can use the test correction sheet if you would like, or you can just make your own, but I cannot give you credit if you don't show me some rationale, some work, as to how you got the correct answer. Let me know if you cannot access your answers. I think you should be able to, but who knows? So just let me know, but that will be due next Tuesday. Reminder. No, we're going to do 2 this time. Reminder that I don't accept late corrections, so just make sure you get those in. I think I have them due at midnight, so that's fine. Okay. Second, labs. So I need to correct the Beers Law Lab still, and I'm going to do that probably tomorrow-ish. So if you haven't got that in and you're finishing it up, get that in, then that'll be done. And please remember, with the lab from this week, the colligative properties lab, I am only looking at the freezing point depression. If you want to do all of them, be my guest. But I don't really talk about osmotic pressure, and I kind of think it's a little repetitive, or I guess like slightly redundant, to do freezing point depression and boiling point elevation. So we're just going to do the freezing point depression. So in the experiment section, you can kind of choose which one. So it's the middle one. You are not responsible for the other ones. You do want to still do like the pre and post lab stuff, but experiment wise, you only need the middle. And I don't think there's a whole lot of materials that you actually need. So I haven't had any issues yet. So I think we're okay there. All right. Lab test corrections. I think that's it. There is a lab for this week coming. So, you know, after this week, I think we get a week off of lab. So I'm going to check the due dates on the labs because we're running a little bit behind with those, but I'm fine as long as we get them, you know, in so that it's reasonable for me to grade by the end of the, you know, semester. So we'll keep working. Beers Law Lab, I would like to have in at the latest in the next day or two. And then Colligative Properties Lab, maybe the weekend, right? Just let me know if you have issues. I'm being very sort of flimsy with deadlines there because I know everyone has their own stuff going on, but falling behind will be bad. So, okay, because it's going quick. All right, so if nobody has any questions about that stuff, let's get into it so we can do some kinetics. So there were a couple questions that I just checked the discussion board a couple minutes ago. So if you just posted something, I probably didn't see it, so you can ask. But I had a question about number 2 and number 7 in the homework, which were two excellent problems to go over. Also, the quiz. I apologize for that, like other random online quiz that I didn't mean for that to be there. That was my bad. Test corrections are next Tuesday. Yes, whatever day that is. What's today? The 3rd. So 3 plus 7 is 10. So the 10th. Oh, quiz. So yeah, if you did that other quiz, it's just extra practice. It wasn't a waste of time. But the actual quiz I will open up tonight at 7. I'm giving you till midnight tomorrow because tonight is a little crazy. And I don't know who's interested in the election and who maybe not, but whatever. I know that, you know, we might want to watch the coverage and whatever. So I'm thinking midnight tomorrow, just have it done. Okay, let's do it. So number 2 from the homework, I am having, like, we're doing construction on our house, hence like the tarp, because it's super dusty over there. So just in case you were like, where is she? Okay, so number 2. We are given a reaction, all right? So the reaction is a very general reaction. Obviously, these are not real molecules. There they are. Okay. What this reaction is telling us that 2 molecules of A react with 1 molecule of B, and they make 3 molecules of C. So that's what this reaction is telling us. So as the reaction happens, B will just react. Every time one of B reacts, 2 molecules of A will react. So you can imagine that, you know, if you have a pile of A and a pile of B, this is A, this is B, and the reaction happens, you're gonna kind of have this situation, right? Because 2 of A is reacting with 1 of B. So if you're making grilled cheese sandwiches and you have 1 piece of cheese and 2 pieces of bread and you have piles of each, after you make 6 or 7 sandwiches, you're gonna have a lot less bread than cheese. And that's because you need 2 for every sandwich. There it is. So that's why when we do our stoichiometric rate expressions, not to be confused with rate equation or rate law, sorry, because why wouldn't all these words be the same? This one's going to react twice as fast. This one is going to react at just a base rate, and this one is going to grow in 3 times as fast because as this depletes and this depletes, that grows in. Okay. Another thing to think about when we are writing these rate expressions This one is going to be negative, and that one is going to be negative because my concentration is going down. It's being used. So though we're taking away concentration units, and this one's going up because that one starts at 0 and then we start to form it, right? So that's why the signs are the way that they are. Okay. Okay, so we need to write the rate expression. So what I'm going to do is I'm going to say the rate is going to equal. Okay, so I know that this has to be negative for A because it's a reactant. Anytime we're talking about rate, it's the change in concentration over time. So if you think about like speed in your car, it's miles per hour. So it's like the distance unit per unit time. So this is just concentration per unit time. They're both rates. They're just measuring how fast something changes over a period of time. All right, so I know that this is going to go down twice as fast. So if I need to find the base rate, I need to cut this disappearance in half because this is going twice as fast as the reaction is turning over. So I need to have a 1/2 here simply because it's going faster than the actual reaction is turning over. All right. All right, and then I'm going to say change in concentration of A over change in time. And there's A. All right, that's also equal to, now I got to do B. So B doesn't have any stoichiometry. B is just base rate. Every time the reaction turns over, B goes down by 1 unit. So I'm just going to say it goes down by a concentration of B over a change in time. Okay, I got to put C on the next line because I ran out of room. So now we have equals. All right, so this one's positive. You can write a plus, so you don't have to write anything. And this is going to grow in at 3 times what the real rate is. So I got to cut it by 1/3. So I got to say, okay, well, C is 1/3 change in concentration over change in time. So that's the little equals is here. So if you think, that's the same equals as that equals, there's my rate expression. Okay. So that was the first part, is just identifying the rate expression. Remember, reactants are going to be negative because you are using them, and these stoichiometric coefficients need to be put into this rate equation so that we get the rate of a single turnover of the reaction. Okay, so now the questions go into finding rates based on other rates. All right, so the first one said if the rate of disappearance of A is negative 0.2 molar per second, what's B? What's the rate of B? That's what it's asking. Okay, here's how we can translate this. The rate of A is this guy, change in A over change in time, right? So I'm going to plug, because if the rate of A is equal to this, then I'm going to use this and I'm just going to plug in. So I'm going to say negative 1/2, but then I can plug in my negative 0.2 molar per second because that's what A is. So all I did is I plugged this rate into this equation. Okay. All right. So now I need to find B. So I'm going to set it equal to, and there's what B is, right? Change in B over change in time is the rate. So this is just going to look like negative X because there's a negative sign here. And this is what I don't know. So that's my X. Okay. Well, that looks like a whole lot easier to solve than the mess above. So I take negative 1/2 times negative 0.2, and then I just got to divide by a negative. I just got to get that out of there, and I get negative 0.1 molar per second equals change in B over change in time. That's how we find that one. So I literally took my rate expression and I just pulled what I needed out of it. So I was looking for the relationship between A and B. B is essentially half of A. So that's what we got down here. Okay. All right. Let me do one more because we got to look for C. Where did my little shoe go? There's my booty. Okay, so now we're going to, I'm going to erase this so that we can solve for C. All right. I'm going to keep my rate expression there because I still need it. There are two ways that we can solve for C. So we can solve for C by using B, which we just got, or we can just go back to A and convert to C. I'm going to do it both ways because they are slightly different and I want to show you how you would do it both ways. So let's say you didn't trust that your answer to B was right, so you wanted to use A. All right, so we got to remember that delta A over delta T is equal to negative 0.2 molar per second because that's what the problem gave us. Okay, and C is right here. C is this guy. So I know that I'm going to take this, I'm going to say negative 1/2, and now I can plug this in just like I did the last time with B, right? That's the same as B, but I gotta find C. So this is positive 1/3 delta C delta T. Okay. So I'm gonna take this out and I'm gonna put a big X because X is easier to see than that other crazy mess. So now we just solve for X. Okay, so I get to multiply by 3 to get 3 out of there. So if I multiply by 3, right, 3 and that cancel. And this then I would just do 3 times. And I get 0.3. 0.3 molar per second equals change in C, change in time. Okay, if you wanted to use B, remember we found B in part 2 or the last part, whatever that was. So that was negative 0.1 molar per second, right? So that's this. So I just got to throw a negative out in front. See that? I'm just solving for C in a different way. You don't have to do both. I'm just showing you both. Okay, well, still, again, 1/3 X. This one seems a little easier just because there's less fraction nonsense. All right, so negative 1 times negative 0.1 is just 0.1. And then you multiply by 3 to get 3 out of there. Hey, it's the same answer. Perfect. So you'll get the same answer either way. It just depends on how you feel like solving for it. All right. Is that all of that one? Yes. Questions? Okay, just don't forget what people do is they forget about the fractions or they'll divide instead of multiply. So just go slow and just be careful with where those are at. Okay, so that's that type of problem. And that was using the rate expression from the stoichiometric equation, the chemical equation. Okay. All right, moving on. Number 7. All right, this had a table. So this just has one reactant. So this would be something like A goes to product. Who cares what it is? There it is. And we have a data table. Okay, so I do 3 separate experiments and I measure the rate of each reaction. Okay, so I have 1, 2, 3, those are my experiments. The first experiment, I use 0.12 molar. I'm going to take my units and put them up top so that makes this a little bit more clear. So the first concentration, I used that much of my A. That's an A. There we Okay, then in reaction 2, I used 0.16 molar. And then when I did it the last time, I used 0.2 molar. So each time I did the reaction, I just put a different amount, a more concentrated solution of A in. And I wanted to see how the rate changed when I added more stuff. Okay, so then we have initial rate. And that's in molar per second because it's a rate and they're always per unit time. And I get 9 times 10 to the minus 3, 1.2 times 10 to the minus 2, and 1.5 times 10 to the minus 2. Those are the rates that I measure each time I do a separate reaction. Okay, so I put my 0.12, I let it go, I monitor at the end, and then I get my rate. You can monitor rate a number of ways, and we can go into that, but that's it's a whole other thing we don't need to do. And then we got 0.16, so I upped the concentration a little bit, and then I get a new rate, and then I up the concentration again, and I get a new rate again. If this was a 0 order reaction, let's talk about order real quick. I find that order doesn't make sense with what order is, right? Like the word order is like, what? Okay. All an order is it will tell us how the rate changes when the concentration changes. So if I have a 0 order, what that means is no matter how much I change the concentration, I could triple it, I could dump all of it in there, my rate is always going to be what it is. It is independent of the concentration of my reactant. A lot of the times these would be like decomposition reactions where something just kind of disintegrates in solution, and it doesn't matter how much is there, it's gonna it's just going to decompose at whatever rate it's decomposing at, and that's it, done. That is 0 order. That means that the rate does not depend on how much stuff is there.
So pretty much it kind of like zeroes it out in a sense.
Say that again, sorry.
So it kind of like zeroes out in a sense, no matter how much you add to it.
Yeah, like it will just, like, let's say the rate was 1.2 molar per second. It doesn't matter how much you add, like that's just what it is, right? So yeah, it will just, like, you've maxed out no matter how much you put in. Does that make sense?
Yes, thank you.
Okay, cool, good. So that's 0. First order is when you double the concentration of a reactant, you also double the rate. So it's saying if I add more, my rate's going to go up by the same amount that I've added. If I add, 1.5 times, my rate's going to go up 1.5 times. So you can change the reaction rate by changing the concentration, and it's like a direct correlation. As you double, you double. That's what a first order reaction is. So if I have A and I double, I should see the rate also double if it's first order. That's what that means. And then second order means that when I double my concentration, my rate quadruples. So now I can just add a little bit more and my rate will go way, way up, right? That's a second order reaction. And that's where we won't go any higher than 2. So it's 0 order, meaning the rate is what it is. Don't waste your stuff. First order is that when you double, it doubles. And second order is when you double, it quadruples. So if you were thinking about exponents, it would be like you'd square it. Okay, so that's what the order is. That's all it's telling you. And the reason why we care is because, one, if you are trying to make a reaction go faster or slower, sometimes you want to slow them down to study them. If you need to make them faster or slower and you know what the order is, well, now you know how to do that in a pretty predictable and effective way. Another reason is because how you deal with the data and how you work up the data to like mean something is going to be different depending on the reaction order. So that's why we care. Okay, so what we're looking for here is the reaction order, and then we're going to find the rate law, and then we can find the rate constant. Okay, so if this was zero order, this number would all be the same. No matter what we changed, this would all say be 9 times 10 to the minus 3. We're not getting any more bang for our buck. That's zero order. But that's not the case, so let's figure it out. Okay, so there are two ways that we can do this. One is just by kind of looking at the table and doing some table logic. Another one is plugging into an actual equation and solve. Neither is wrong. It just depends on what works better for you. So I'm going to plug it in first. So what we're really doing is we're going to say, okay, well, the rate is going to equal to K times my concentration of A to some number. And I don't know what that N is. That's my order. I don't know what it is. So it's an unknown. So I'm going to take this equation and I'm going to compare two experiments. Experiment 1, 2, and 3. I can pick whatever I want. I picked 1 and 2. You can be wild and do 1 and 3. You could do 2 and 3. It is totally your call. They will all work because we only have one reactant. So you go to town. Okay, so I don't like decimals. Like I don't like fractional numbers if I can help it. So I'm going to take a bigger one. So I chose to take experiment 2 and I'm going to divide it by experiment 1. Okay, see that? So I'm just taking experiment 2. There's my rate law that I don't know. And I took it over experiment 1 and there's my rate law that I don't know. So K is the same. So that cancels out. So what I'm going to plug in is the rate for 2. So that's 1.2 times 10 to the minus 2. And I'm going to put that over my rate for experiment 1, which is 9 times 10 to the minus 3. You don't have to like write all this stuff out. I'm just writing it out so you see where I got it. Okay, K I'm going to ignore because it's all the same and who cares. All right, so now I need concentration. So I'm going to put 0.16 on the top because that's experiment 2, right? I put 2 over 1. And then on the bottom, let's see if I can switch this light here. Okay, that's better. On the bottom, I'm going to put 0.12. And then this N is going to be the same. So now I look for that. Okay, so how do we do the math? Let's divide. So I'm going to divide 1.2 times 10 to the minus 2 over 9 times 10 to the minus 3. And I get 1.33. Okay. Then I take 0.16 and I divide it by 0.12 and I get 1.33. All right, so when I'm looking at this exponent, it's just 1. They're the same number. This number to the first power is that. So don't be thrown off if you don't get whole like regular integers there. It's okay. If they're equal, then that's just 1. All right. Okay, so since I know that n equals 1, this is first order. Because as I increase this by some amount, this also increases by the same amount. So it's first order in A. So that little n is a 1. Okay. All right, so where's my sock? Here it is, my little slipper. All right, so now that we know what order this is, now I can fill in my rate law. All right, so I'm just gonna erase this bottom. I already did this on a piece of paper and you know I always post it, so don't worry if you didn't get it all written down. Okay, so my rate law now, I can fill in that little n. Rate law equals. All right, so when you write a rate law, this is always how you want to set it up. Rate equals K, and then you put in your reactants. Our reactant is A. If there was another one, you just put the other one in, and you got to add the exponent. Now, do you have to put the 1? No. You could leave it out. If there's nothing there, we just assume that it's 1. But if you want to put the 1 because you found it out and you're proud of yourself, then put the 1. Okay? So there's my rate law. It says that my rate is equal to my rate constant times the concentration of my reactant and its first order. Okay. I'm going to finish this and then I'll play with my rate law for a bit and we can talk about other things. Okay. The last one is they ask for us to solve for K. So what I do is I take the first line of my data table. Why? Because if I looked for another line, I would write the numbers down incorrectly because that's just the way that I roll. So I just like to take the first line and I put the rate, 9 times 10 to the minus 3 molar per second, is equal to my unknown X, and then we have concentration of A. So what I'm going to do is I'm going to divide by concentration of A so I can put that under here, and I get 0.12 molar. Okay. So when you divide, I get 0.075. It's first order. See how that is gonna cancel with that M, so the molarities cancel. So my units are 1/seconds. That's first order unit for K, and that's my K. And that's what they wanted me to do. Okay. So again, to get these values, I literally just copied them from my data table. I didn't do anything fancy. And if you did it with experiment 2 or with experiment 3, you'd get just about the same number. Kinetics never works out perfect. So if you're off by a small decimal, it's not a big deal. That's just life in kinetics land. Okay. I'm going to quickly just talk a little bit about the rate law and overall order really quickly. So let's step away from this one. All right. Let's say we had A plus B goes to AB. Okay. So now I have 2 reactants. So I would have a data table and then initial rate. All right, so here's my fake data table. So this is what it would look like. I'm not going to be able to get like numbers that come out right. So I'm just going to like theoretically show you. All right, so let's say this is 0.1, 0.1, 0.2, and this is 0.1, 0.2, 0.1, right? Does that make sense? Yes, yes, hooray. And then, you know, let's just say this is 1, this is, yikes, whatever. I'm not going to go there because I'm going to spend too much time like fuddling with numbers. Okay, so I just want to show you because this is confusing. Let's say I wanted to find the order in A. Which equations, which trials do I use? This I can't be so willy-nilly about which one I choose, because if you are going to analyze how the rate is affected by the change in my reactant A, I need to make sure B's doesn't change. Because if you look at two experiments and B also changes, then how do you know that the rate change is due only to A? You don't. There's no way to know. So what I'm going to do in order to solve for A, I need to find 2 experiments where A changes and B does not, because I'm looking for A. So I want B to cancel out. So in order to do that, I can't use 1 and 2 because A doesn't change, so that's not going to tell me anything. So I have to use something where A changes. So I could either use 1 and 3 or 2 and 3. If I use 1 and 3, B is 0.1 and 0.1. So it doesn't change. If I use 2 and 3, they both change, and I'm not going to know. It's going to be a big mess. So I would use 3/2 or 2/3. It doesn't matter how you do it. It's fine. And I would just go ahead and solve for A because B would not be involved because B would cancel out just like K would. So I would just say rate, I would do rate of 3 over rate of 2, whatever that came out to be. And then I'd say 0.2 over 0.1 to the whatever. All right. And let's say, so this obviously is 2. Let's say this also came out to be 2. Then I would know that it's first order in A. Okay. That's just like we just did, except we had to be a little bit more picky about which one we chose. Okay, so let's find the order in B. All right, so now I'm looking for order in B. Now I need A to go away. All right, so B has to change, and A, I want to just pretend like it's not there. And the only way to do that is to make sure that it doesn't change in the two equations that or in the two experiments that I choose. So for B, I could either do 1 and 2 or 2 and 3. Again, if I chose 2 and 3, this guy also changes, so that's no good. But if I took 1 and 2, B doubles, 1 is constant, so I know that any changes between experiment 1 and 2 is going to be due to B alone. So I would do, okay, rate of 2 over rate of 1 equals 0.2 over 0.1 to some power. Let's say this came out to 4, and this was 2. 2 to the what power is 4? 2 squared is 4. Oh, hey, this is second order because that little n is now squared, right? So that's how I would tell that one of them is second order. If, if it was 3, it would be 3 to the n equals 9, right? 3 squared is 9, okay? That one's second order. So now I can write my rate law because I found that A is first order and B is second order. So my rate law looks like this. Rate is equal to K, A, B. Now I got to put in my orders. A is 1. You can put it in or not. And B is 2. So that's what that rate law looks like because we found that A was first order and B is second order. Well, what's my overall order for the whole thing? You just add them. So if I need overall order, it's 1 plus 2. 1 because A is first order, 2 because B is second order, so it's third order overall. And we don't really need to do anything with that number, but now we know how to find overall order if you need to. Where that's most important is when you have 2 first orders, which comes out to a second order, but then you can like manipulate the reaction so that it's really first order, which makes it much easier to deal with. And again, that's a story for another day, but that's kind of why we care about overall order, just in data manipulation. Okay. I have one more thing that I wanted to cover, but let me know if you have anything on the data table stuff that you think while I erase my board. All right. Awesome, you guys. Last one is the graphs. The graphs always throw people off. And I sort of don't know why, because not because it's not, kinetics is hard. I did kinetics for a really long time, which is why I enjoy this, because I've actually like physically did a lot of kinetic experiments. But this is not easy stuff either. So the graphs, all you have to know is that the graph that you want is a straight line. So if you're given 3, I'm never going to make you graph something on an exam. It's too time consuming, and we graph in lab, and I'm not going to give you data points to graph. I'm not saying you don't need to know how to graph. I'm just saying I'm not going to test you on graphing. But if given a couple graphs, what you have to do is just say, it's that one. That's all you have to do. So what you want to do is find the straight line. Okay. All right. So I have 3 graphs. There they are in their glory. I have time on the Y, and what changes is my x-axis. So depending on the order, you will change what you're actually graphing. So for a 0 order reaction, you just graph the concentration. All right. For a first order, I didn't leave myself enough room. You do the ln. And for a second order, you do 1 over the concentration. It's just because of how the rate laws are integrated, which next week, this coming week, you'll do integrated rate. I don't make you integrate them, but you use the integrated rate law. So that'll be a little bit more obvious to you once you've done them a few times. All right, so there's my 3 things that I need to graph. And all I'm doing is comparing. So I'm gonna lay out all my graphs. Like I would give you kinetic data, and it would be time and concentration. And you would graph that 3 different ways. So the first way would just be concentration versus time, just like I gave you, graph it. The second one, you'd have to take the ln of your concentration and graph that over time. The third one, you would take the concentration and take the inverse. So you do 1 over and just graph it versus time. So they're all based on the concentration data, just manipulated a little bit differently. Now, if we had something like this, you say, where is my straight line? The middle one, spoiler alert, is my straight line. This is a first order graph because it's the ln one. So that you kind of want to remember. But once you do the integrated rate law enough, I feel like it becomes a little more obvious. So that's my first order. That's the line. So if I was like, here's my data, what order is my experiment? You'd be like, that's a first order experiment because the line is straight on my first order graph. This one's 0 and this one's second. Okay, so let's say now we had a new reaction. Now we find the straight line. What order is my experiment? Oh, my experiment is my straight line. That's a second order graph because my axis is 1 over A. So that's second order. That's all you have to do. So if for that first example I had where we had rate is equal to KA, right? We know that's first order overall. So you'd look and it would be like, which graph is it? Oh, it's this one because this is first order. That's first order. So you'd say this graph is the appropriate graph. That's it. I'm not going to make you graph. You just have to identify the correct graph. And you're going to do that by looking for the straight line and then either knowing or making an educated guess on which one it is. So 0 is easy to remember because there's 0 other things there. It's just the concentration, 0 extra things. And then first order is your ln and second order is your 1 over. That's the deal with the graphs. And that's another way that you can identify the order of a reaction. And I think those are the only 2 ways that we've done order. There's also mechanisms, which comes this coming week, is looking at the mechanism, but we don't need to worry about that this week. So I think that's all from this week. What else we got? Anything else? I'll let you think for a sec, just in case, because we have a couple extra minutes and I have no problem ending early, but I just want to make sure I get everybody covered, ready to go. There was some posts on the discussion board about rate orders and then about kinetics versus thermodynamics, which if you have questions about that, I tried to, put like a novel. I tried to not make it too long, but on those topics. And so you can always go there if you have questions about that. April, did I answer all your questions? You're always creative with your questions.
Yes, you did. Sorry.
Okay, don't be sorry. I enjoy answering your questions, so I wanted to make sure I covered all the things.
I try to think of them like on a different level, so this way I understand them.
Yeah.
And the only thing that like really got me was that I saw that like in number 5 on the like the in-class problems was that just like the reactants just were like, no, I'm done. Almost.
The reactants were what?
Like they just finished reacting and then they were just there.
Yeah. So if you have leftover, so the reaction that she was talking about, it was like an A plus B goes to C, right? Where you're just like, or C plus D, but whatever, we'll keep it simple. And it was 2B. So it depends on which one is your limiting reactant, which is a Chem 1 thing, right? So it depends on who runs out first. So like the grilled cheese analogy where you have a stack of cheese and a stack of bread, and when you run out of bread, you can't make any more sandwiches. Even if you have cheese left over and you could potentially make more sandwiches, if you don't have any more bread, there's no more sandwiches. So your little sandwich factory comes to a halt. So that's the same thing that happens with a reaction. So if you have one of your reactants, it doesn't matter which one. In this case, B would run out first because you have to use 2 of them for every time you do this reaction. So if B runs out, everybody just kind of sits there. So your product just kind of hangs out and the extra A is just there. If you left it out long enough, sometimes you can get side reactions, or it will react with the atmosphere sometimes depending on what chemicals you're using, but it just stops. Everyone's just kind of like, well, we'll just hang out because there's no more molecules to be making and breaking bonds and making new things. A can't make a new thing if it's just by itself, if it was originally supposed to be reacting with B and B's gone. You can put equimolar amounts of things so that once they all react, there's no more A and B, and you just have your product and he's there by himself and you're good to go. You can definitely do reactions that way. When things get tricky is when you have an equilibrium. So now you have, when you run out, you never really run out because you have that, kind of constant back and forth, which is the next chapter. But when you have just a straight arrow and reactants are just forming product, after you run out of one, it's like, we're done. And your reaction is considered over. And then you would have to separate out your product and, eat your grilled cheese. Does that help?
Yes, it does.
Oh, good. All right, friends. Anything else? All right, I will put this recording up. I will put all the work I have on my piece of paper. I will get you some due dates, and I will remind you about test corrections, and I'll send it in a little announcement. So just watch for that for later. Listen, I will let you go. Enjoy. Let me know if you need anything, and I'll post all the things for you. So
Okay.
thanks, everybody.